I think it was fantastic. We were able to get Martin's presentation up there. Many of the topics that he presented, I will touch on as well. Martin gave an excellent kind of setting the framework for a lot of these concepts that we use in generating the kinematic rupture. So I'm Robert Graves. I'm with the U.S. Geological Survey in the Pasadena office. What I'm going to present here, as I alluded to, I draw from many others. In particular, I'd like to acknowledge input that I've gotten from my longtime collaborators, Arvind Patarka and Art Frankel. So let's just get right into it. So just an outline of what I'm going to talk about. I'll go through some of the basics of kinematic rupture characterization. Martin touched on this, but just to make sure that everybody's kind of on the same page. Two particular topics that I want to get into, slip characterization, including shallow fault effects. And what I'm going to propose is a hybrid model where we combine long wavelength shallow features with short wavelength deeper slip features. And then the second topic is guidance on how to choose or what is the appropriate subfault size given the maximum simulation frequency, our target frequency. And I'll show a kind of a simple relation that I've come up with some empirical analyses in order to provide that guidance. So just actually, even before I get into the basics on the kinematic rupture, and Martin talked about this, there's kind of two ways to do this problem. The dynamic rupture model, which I'll say is the right way, it adheres to the physics. It describes the underlying physical features of the problem, the state of stress, strength of the rocks, and frictional properties, et cetera. And then rupture just occurs spontaneously as the frictional strength is surpassed by the imposed stress. There's a lot of parameters that need to go into this, and they're difficult to constrain, and it's also a difficult computational problem. It's getting easier, as Martin alluded to, but it's still a little bit more at the forefront. On the other hand, the kinematic rupture model, it just describes the movement of the fault, but does not directly address the underlying physics. So the fault rupture is simply prescribed by the slip time function that occurs at each point on the fault. And so that's what I'll talk about here. And currently, when we do many of these large-scale simulations, we're using this kinematic rupture model or kinematic rupture description. So the basics, what do we need? We just need the slip at each point on the fault for the entire time of the rupture. In order to get that, we need to prescribe the fault location, the fault geometry, the dimensions of the fault. We also need to know the seismic moment or the magnitude of the earthquake and the hypocenter. And Martin talked about some rules that we could use to maybe get some guidance on where to put the hypocenter, for example. We also need rules for actually specifying the slip distribution. So here's an example. This is just one rupture realization that I generated, and I'll talk a little bit more about some of the rules for that in a moment. Okay. All right, so this is an example rupture that I generated. We start with a slip distribution, and then we need to know how does the rupture actually propagate. So we can specify a hypocenter location. Okay. So we need to describe how does the rupture propagate across the fault from the hypocenter. So we have rules to specify what is the rupture speed. The contours that are shown here, the black lines, show the rupture propagation fronts. You can see there's some complexity there. There's stochastic features that are added in. And now, how does the advanced slide work? Doesn't.
Working? Okay.
What?
Okay. Yeah.
Okay, can I go? There we go. Okay, so as the rupture gets to a particular point on the fault, the slip occurs. The red curve here is the slip rate function. That's the time derivative of the slip at that point of the fault. Martin had showed some examples of this. It's typically what I would call a front-loaded time function. It has a sharp rise in the beginning and then this kind of longer tail. The rise time, Martin referred to rise time. That's the total duration of the slip at a single point on the fault. I'll refer to that a little later on in the talk. Keep in mind that the slip rise time is much shorter than the total duration of the rupture. Slip rise time is typically on the order of a second or two. Total duration for a magnitude 7 earthquake could be 15, 20 seconds. For a larger earthquake, it could be many tens of seconds. So how do we specify this heterogeneous slip characterization? Pseudodynamic approach is kind of what Martin had described, where the kinematic parameters are constrained using dynamic rupture statistics. You do a lot of dynamic ruptures, you look at the statistical properties, and then you can develop these models. The other approach, spatial random fields, constrained by slip inversions. Martin also talked about this. And that's what I've used in the kinematic rupture generator. So the slip inversion wave number spectra are used to derive correlation lengths and the high frequency fall off. And as Martin had indicated, the wave number spectra for the slip generally falls off as k to the minus 2. There's several models that have been developed, and Martin talked about these, Somerville, the Mayan Barossa, and then most recently, a model by Suzuki et al., which incorporates additional data from a number of Japanese earthquakes. I'm showing with these relations the correlation length that is predicted as a function of magnitude. So they're very similar, although the coefficients in these models are a little bit different, and I'll show the kind of the implications of that in a couple slides. Martin had also talked about the different types of autocorrelation functions that are used. The von Karman appears to be kind of the best suited in terms of fitting these slip inversions and coming up with a function that represents that correlation length. So in much of the modeling that I've done, I've used the Mayan Barossa model, and I'll refer to that as MBO2 in the next few slides. So here is another example of the slip distribution that's generated for magnitude 7 earthquake. The correlation length for these slip patches is about 10 kilometers, and you can see there's high slip, there's low slip. It's randomized, but it is still adhering to this correlation. This particular model I've used for a number of earthquakes, also comparing it against ground motion models. The plot that I'm showing here on the lower right is a goodness of fit plot looking at the average fit to observed records across 12 California earthquakes, magnitudes 5.9 to 7.3. So the zero line there is a perfect fit. The average, the red line for the model is generally close to that, although the dispersion is also indicated as well. We don't fit every record exactly. I mentioned this most recent model, Suzuki et al. It has a different coefficient in the correlation, and that leads to a longer wavelength distribution in these slip patches. So the plot on the left here, the middle left, it has the same phase distribution of these slip patches, but it's using a different correlation length. In this case, it's about a little over 60 kilometers. And it's basically, you could think of this as kind of a long wavelength of filtering on those. In the simulations that I've done, I found it's kind of difficult with these longer wavelength slip patches to generate the same kind of intensity for the strong motion levels. However, if we think about just the slip distribution along the shallow fault, there are some differences between these models that kind of go in the other direction. So MBO2 has this kind of quasi-periodic distribution of slip. And what I'm plotting here is the slip just right at the top of the fault, kind of like if a geologist went out and measured that in the field. The bottom plot is showing for that same slip model, but using the SEA22. And it has this enhanced longer length scale features, which is actually more similar to what we see for observed earthquakes. I haven't done a detailed quantitative analysis, but the plot on the lower right is the slip distribution measured along the surface, the displacement for the magnitude 7.1 Ridgecrest earthquake, 2019 Ridgecrest earthquake. And it looks generally more similar to the SEA 22, kind of this broad, long length scale slip, maybe with a couple of peaks superimposed on that. Okay, so the idea here, well, the idea is that there's different kind of characteristics of the ruptures as you go from the shallow part to the deep part. It's been observed that shallow part generates weaker high frequency motions. The 2011 magnitude 9 Tohoku earthquake is a classic example of this. Dynamically, this is modeled as velocity strengthening or low to negative stress drop. But kinematically, you can model this reduction of rupture speed, lengthening of rise time, or as Art Frankel has done, superimposing high stress drop subevents on a smooth background slip. So kind of taking from those ideas and just looking at the slip distribution, what I'm proposing is a hybrid model that combines the MBO2 and SEA22 models to further account for this depth dependence. So the very shallow part of the fault uses the long wavelength, SEA22, and then that transitions to the MBO2 on the deeper part. And the bottom plot here on the left just shows that combination. It's a very brute force, simple approach, just a linear kind of interpolation in the middle part of the fault. Using that approach, I went back and I reevaluated the validations, again, because the strong motions are controlled by the deeper part of the fault. The fit to the observed motions is very good, but now it also has this characteristic that if you look at the shallow part, it does tend to have these longer wavelength features. So that looks promising. Okay, the second part that I'd like to talk about is the subfault size and the frequency resolution. So the idea is that given a maximum resolve simulation frequency, say 10 hertz or 5 hertz, what is the maximum subfault size that we can use on these kinematic prescriptions that accurately represents the source? And the way I'm going to investigate this is I'm just going to look at a suite of magnitude 7 ruptures having different subfault size. So I'll start with this example here. The subfaults here are actually very small, 20 meters. Okay, so the total fault length is 60 kilometers. We have a large number of subfaults. These are just individual patches where we've defined the slip, the rupture time, and the slip function. Now, in order to kind of look at the resolution, what I've done is I've taken all of those subfaults and I compute the moment rate function. So the moment rate function is computed by going at each subfault, take the slip, compute how much moment is released as a function of time, and then sum that across the entire fault. And in summing across the entire fault, you take into account the rupture delay as you go across the fault. So it's kind of a simplified representation of the entire rupture. The middle panel here shows that moment rate function. And you can see it goes on for about 20 seconds, right? That's how long it takes for the rupture to take place. The right panel, I've computed the Fourier amplitude spectrum of this. Okay, now just to compare against a theoretical model, G and Archuleta have a model that's shown by the black curve, agrees rather nicely. In particular, the high frequency fall, if this is what I'm going to focus at, I've actually incorporated a time integration here, so it's in the plot, it goes as omega to the -1, but this is consistent with an omega to the -2 model. And that's what Martin had talked about. One of the guiding principles in these models is that we want the high frequency fall off to go as omega to the -2. And in this particular case, it agrees nicely all the way out to about 10 hertz or even further. Now, just to kind of get some statistical sampling, I've considered multiple realizations shown here in the different colors, and they all agree very nicely. Now let's look at a larger subfault size, 100 meters in this case. The middle panels show the plots for the moment rate function, and visually they actually look pretty similar. But there are differences, but they're rather subtle, and they show up most significantly when we look at the spectrum, the plots on the right. So on the bottom right, you can see that we get this bump out at the higher frequencies when we use larger subfaults. And this is maybe somewhat intuitive in that there's a spatio-temporal kind of aliasing effect that happens here. Basically, as the subfaults get bigger, at some high enough frequency, you're actually seeing the individual subfault go on and go off, go on and go off, go on and go off, right? And so that creates these artifacts. And we don't, if we're modeling up to those high frequencies, we don't want some, an artificial kind of feature to come in, right? We'd rather have it be something that's embedded into the rupture. Okay, so in order to develop a very simple rule of thumb for this, I repeated the process for a number of subfault sizes, and then I just took the ratio of the Fourier amplitude spectra to the 20-meter case. So I'm going to kind of say, well, that 20-meter case looked pretty good out to 10 hertz. Where do these other cases start to deviate from that? And those are shown in the plot here. There's a very systematic deviation or increase, or I should say decrease in the frequency resolution as you increase the subfault size, which makes sense intuitively. Just to kind of develop a rule, I took just measured where do things deviate by about 10%. And then I plotted those points on the right. So the vertical axis is subfault size. The horizontal axis here is actually 1 over the frequency where that deviation occurs. And you can see there's a systematic character to those points, just fitting a line through it. And again, this is not super rigorous, but it results in a rule of thumb here where the subfault size is related to the inverse of that frequency. The coefficient here turns out to be, it has units of velocity, 200 meters per second, and I think there's a physical relation here that is probably around the lowest velocity of rupture across the fault. So, in order to, if that occurs, in order to have the resolution, you need subfaults that are finely spaced. So in summary, there's actually 3 points here. Proposed hybrid kinematic slip model that combines the high or long wavelength shallow slip with short wavelength deeper slip patches. This model appears to do well matching the observed strong motions and the shallow slip characteristics. The second point, I didn't actually talk about the details here, but Martin alluded to this as well. It has to do with the rise time. And there's got to be some correlation between the rise time and the local rise time and the local slip amplitude. It looks like a model that has a rise time correlating with a slip with some randomness. That results in roughly constant slip rate, and that looks like it provides the best agreement with the dynamic models. The last point, which I did show some results, the empirical test providing guidance for the kinematic subfault size, and this rule of thumb is the Hmax is proportional to 1 over the Fmax with a constant of proportionality 200 meters per second. I will say this results in a lot of information that has to be stored about that kinematic rupture. And this, I think, presents another challenge in that we need to come up with ways to efficiently describe that if we want that level of detail, especially if we're talking about magnitude 7.5, magnitude 8 earthquakes. So I think there's some opportunities for improvement in efficiency and maybe some research ideas. Also, all of the above will benefit from further testing and validation. Validation is the key. We need to maintain or build confidence in these models. And again, just reiterating something Martin said, particularly to ensure consistency with the dynamic models. And that's all I have. Thank you very much.